Okay, so let's talk about bias and variance, which is another view of approximation versus generalization. Okay, so the bias, variance analysis. Okay, and let me contrast this a little bit or show you how it's related to what we just did, which is what's called the VC analysis, which gave us this generalization error bound that links E in to E out. So in the VC theory, okay, there were two important quantities, which was E in, how well did you fit the data. Okay, and then, so that's one aspect of the trade-off. You'd like to get that low. And then there was the E out versus E in issue. So E out is approximately equal to E in. So how close is what you did do? How close is what you see? Is what you did to E out. Okay, and what you did, you can measure. Okay. Now the bias variance analysis, sort of similar but different. So instead of E in, instead of how well did you fit the data, we can look at a specific problem and ask the question, how well can you fit the data? So how well can you fit? Not how well did you fit, but how well can you fit? Okay. So in some sense, there's some deviation between the hypothesis set and the target function. Okay, so imagine that the target function is living here, and there's your hypothesis set with a bunch of hypotheses. Each dot is a hypothesis. Okay, and in some sense, there's some best hypothesis. Okay, so in some sense. Okay, in some sense. Okay, and this is roughly speaking how well you can fit the data, and this is what we call the bias. Okay, so this is the bias. How well can you fit the data? Okay, but then similar to the question of how close is what you did to what you care about, which is E out. So this is how well you can fit the data. Okay, that establishes a bias. But then you now also need to find this guy. Okay, so how well can you find the best guy? Okay, so how easy is it to find this, best function, in some sense best function, the best function. And what do we mean by that? Well, what we mean by that is, there exists sort of how well you can do, okay, but now you have to find it, and the only thing that you have that allows you to find this guy is the data set. So when you generate a data set, okay, you'll try to go to the hypothesis in your hypothesis set that looks best on the data set. So it might be this guy, okay, and on another day, if you generated another data set, the hypothesis that looks best is this guy, and then this guy, and then this guy, and so on. Okay, so any particular data set is going to result in not finding the best that you can do, but finding whatever you happen to do on the data set. So depending on what data set is generated, there's variance in what you output. You'll not usually be outputting this sort of hypothetical optimal guy that accomplishes the best you can do. Okay, but now, so this is a sort of a heuristic picture of what's going on. So there's some variance around that best guy, okay, and we can already start to sort of think that the larger a hypothesis set. So if I make my hypothesis set larger, okay, now the best I can do is F. So then the bias drops to 0 for larger hypothesis sets. Okay, but now that the hypothesis set is larger, if I have a given small data set, now, on any given day, if I generate a small data set, there's going to be something that gets 0, and that's something that can get 0, and another guy gets 0, and 0, and 0, and 0. And so for a small enough data set, I'm going to be going all over the place in this hypothesis set. And so it's, even though the best I can do is, close to the true target function, it's very hard for me to find that on the basis of a small data set. And so that's this variance at play. Okay. So let's quantify that. And I'm gonna sort of illustrate all the ideas with just a simple example, and then we'll, see some experiments and we'll summarize. Okay. So let's consider, and okay. So before we consider the example, let me just mention that, so this is a beautiful general theory. Okay. This bias variance analysis, the first limitation is that it only applies to squared error. So which includes the classification error as a special case. So what do we mean by squared error? So you measure the error between h of x and y, which is f of x, by h of x minus f of x squared. So in classification, the classification error is related to the squared error because, if you take the squared difference between +1 or -1, when they're equal, the squared difference is 0, and when they're not equal, it's 4. Okay, so it's proportional to the squared error. So bear in mind that our discussion applies only to the squared error, but then people like to, use this sort of heuristic analysis that says that, it's good to reduce the bias. Reducing the bias amounts to sort of improving the best hypothesis in your hypothesis set. So generally speaking, increasing the size of the hypothesis set, and reducing your variance is sort of reducing how wild, in some sense, the hypothesis that you do output, the final hypothesis that you do output, is on the basis of a finite data set. Okay, so this heuristic analysis can be sort of thought of as valid in general, but technically, mathematically, the bias variance analysis applies to squared error. But there is a good news. Okay, so it can take into account the algorithm A. Okay, what that means is that the same hypothesis set with different algorithms can result in a different bias and a different variance. Okay, and to contrast with the VC analysis applies to any algorithm, so it had to be necessarily loose. So sometimes the bias variance analysis gives us a slightly sharper view of what's going on in this approximation generalization trade-off, because it can take into account the algorithm. And you can imagine why it's important to take into account the algorithm to get better bounds, because suppose your algorithm is kind of stupid and it always picks hypothesis H1. Okay. The VC analysis doesn't know that, so it gives you a bound for the whole hypothesis set. But effectively, your hypothesis is just H1. Your effective hypothesis set is just H1. So, H1, and so it has a huge bias, but very little variance. In fact, zero variance, because when you vary the data set, there's no change to the hypothesis that you output. Okay, and so this analysis can take that into account. So let's consider an example. The example is a very simple example. Okay, so imagine that I have a target function, and I'm going to put the target function in red. Okay, and I'll draw it twice. Okay, and you'll see why soon. So I have a target function, and I'm going to draw it twice. Okay, and imagine that I have a data set of size 2. So I'm going to generate a data set of size 2, and I'll generate it twice. So it's not that I'm doing the experiment twice. I'm just repeating the drawing of the same experiment twice. And now this is where the two experiments are going to change. Okay, I'm going to now have a particular hypothesis set, which is lines. So it's easier to describe the concepts in the context of regression. And so we're doing regression, not classification. So think of this as, this is f of a one-dimensional variable x, and this is x. So this is f of x, and this is x. Okay, and now, I'm gonna try to use this data to learn a final hypothesis, a G that approximates f. But now I need to tell you what the hypothesis says. So I'm going to consider H0, which is just flat lines. So lines with zero slope. So the only thing I get to do is change the level of the line. Okay? And then here I'm going to have lines with slope. H1 equals lines with slope. So if I look at the number of available parameters here, I just get to pick one parameter, which is the level. So one parameter. And here I have a line where I get to pick a slope and an intercept, so I have two parameters. So just to illustrate, you know, the learning problem in this regression setting with two different hypothesis sets. They're very simple hypothesis sets, and I've chosen them so that one is clearly more complicated than the other. Okay, so now what's a reasonable algorithm? Find a line that minimizes, since we're working with squared error, find a line that minimizes the squared error to the points. So a line is a function, you know, g of x, that's constant. So what's the constant that's going to minimize the squared error? It's the average. Okay, so if I learn with this data set, I'm going to output the average. Okay, so this is my g of x for this data set. Okay, and if I learn with that data set, well, since I have both you know, intercept and slope, I can fit the data exactly. Okay. All right. Now let's examine some sort of you know, properties of these two. So this is, let's call this g sub 0 of x, and let's call this g sub 1 of x. Okay, so now, so that's what's going on in sample. Okay, now I generate a test point. I generate a test point x, let's say somewhere here. So I generate a test point x. Okay, and you know, now this guy is going to predict. So here's my test point x. Okay, so this guy predicts, you know, g sub 0. So let's just call this g0 of x. Okay, and this guy predicts, you know, g. So this point here is g0 of x. This point here is g1 of x. Okay, and this guy here is the error. Okay, so what's the error? The error is f of x minus g0 of x squared. So that's the error. And here we have a much smaller error, it looks like. Oh, fantastic. Okay. So let's call this f of x minus g1 of x squared. Okay. So that's the situation that appears with, you know, a particular data set. You know, you fit, you get your final hypothesis, you predict, and you get two errors. Okay. Now I want to see what happens. Well, you know, the data set is random, and this is just one particular realization of the data set. And you can imagine that, you know, and it looks here that, oh, wow, you know, why would you ever go for the flat lines? Okay. Why not go for the lines with slope? Okay, so let's see what happens if I had generated a different data set. I'm going to make that data set blue. Okay, so here's a different data set. I'm going to generate that point and that point. It could happen by accident. Okay, I mean, the data set is randomly generated. You randomly generate x values. So that's this point and this point. Okay. Now, in this scenario, what's the function I learned? The flat line that, you know, sort of best approximates these two, i.e. its average, is somewhere here. Not too different. Okay, and approximately the same error. Okay, and the line with slope that fits this blue curve is this guy here. Wow, look at the big difference. Okay, look at the big difference. So now this error became huge if I predict at this test point with this g1 of x versus this g0 of x. Okay. Here the error has stayed approximately the same, and here the error has suddenly become huge. Okay, so if we're going to analyze each of these hypothesis sets, okay, so which data set should we pick? There's no reason to pick this data set over that data set. We don't know what's going to arrive in practice. So we should analyze, in some sense, the entire random process of generating the data set, followed by fitting, followed by computing the error on a test point. So we want to know what's the expected behavior with respect to data sets. Okay? So, let us analyze the expected behavior with respect to data sets. Okay, so expected behavior with respect to data sets. Okay, so here's the process. Okay, you generate a data set, and it could have been either the black or the blue. So you generate a data set, and let's imagine that we generate multiple data sets. So we could have, in this case, we just generated 2 data sets. So you generate a data set, D1, D2, D3, up to D sub m. Okay, and then from each of these data sets, you would learn a different function. So you know, the blue or the black, but in general, for different data sets, you learn a different function. So let's call this, you know, G, okay? And in order to emphasize that I learned this from the data set D1, I'll call this GD1. So I'll use the superscript D1, okay? GD2. So we produce a different final hypothesis, okay? And then we can now evaluate this final hypothesis on a test point. So we get GD1 of x. So imagine this test point is fixed. GD2 of x, GD3 of x, GDM of x. So I've generated m data sets. Okay. And now you can see that depending on the data set, I get different hypotheses, and then for each hypothesis, I get a different prediction on x. So we could ask, what's the average prediction? So the average prediction, let's call it G bar of x, is the average, is 1 over m, the sum from I equals 1 to m, GDI of x. That's the average prediction. Okay. And we know from, you know, basic probability that this average, if we were to take this in the limit of large enough m, this is approaching statistically approaching the quantity, which is the expected value over data sets. So this approaches the expected value over data sets of GD of x. So think of a random process where what's random? The randomness is coming from the data set. So you randomly generate data sets, you produce a hypothesis, you evaluate it at x, and now you compute the expected value with respect to the randomness, with respect to the data set. Similarly, we could be interested in the variance of the predictions. So let's call that the variance at x. Okay. And so this is equal to, you know, the sum. So if I compute the variance of these guys, it's 1 over m. Okay. The sum is the average of the deviations of each individual prediction from the average prediction. So it's the sum. It's the average of the deviations. Okay. So GDI of x, it's the average of the deviations between the actual predictions and the average prediction, minus G bar of x squared. And this is where the squared error comes in. Okay, so this is the variance. Okay, and as I take the number of data sets larger and larger, this is just approaching the variance. Okay, so it's the expected value. So this is an average. So it's the expected value over data sets of the quantity GD of x minus G bar of x squared. Okay, so this is the expected prediction. This is the variance of the predictions. Okay, and now let's look at the error. Okay, the error. Okay, so the error. The out of sample error, so out of sample error is, for each of these, is, you know, f of x minus GDI of x squared. Okay. That's the out of sample error for each of these. So we could ask, well, on average, what's the out of sample error for this process that, generated the data, then you picked a hypothesis, and this is where your hypothesis set and algorithm come in. And then we evaluated the hypothesis on a test, evaluated these hypotheses on a test point, and now we compute the average error. Okay, the average error is 1 over m, the sum from I equals 1 to m of the squared differences between f and g. And again, the squared error is playing a role here. Okay? Now, it is a well-known fact from, probability theory statistics that the average deviation between a constant, so f of x is a constant, okay? F of x is a constant, and g is what varies when you generate different data sets. Now, it's well known that the average deviation between a random variable and a constant, when you square it, okay, so the average squared deviation between a random variable and a constant is equal to the squared difference between that constant and the average value of the random variable. So this guy is equal to the squared difference, so it's equal to 1 over m, it's equal to the squared difference between f of x and g bar of x. Okay, so f of x, it's just a constant. It's the target value at this test point. What's changing with I? Changing with I is your predictions. So the squared deviation, the average squared deviation is the squared deviation between the constant and your average prediction plus the variance in your predictions. Okay. That's a well-known fact from statistics, probability theory, and you can go and derive this if you want. I won't. You can see the derivation in the slides. You can see the derivation in the text. Okay, and this we call the bias, little bias at x. Okay, the bias at x. Okay, it's the squared deviation between your f of x and your g bar of x. And so we see that your out of sample error, E out. Okay, so theorem, I'll write this down now as a theorem. It's a decomposition of this error. So theorem, and I'm using a big word theorem, but we just derived it, theorem. Okay, so this is your average out of sample error. So, and this for large enough m becomes your expected out of sample error. Expected with respect to what? Expected with respect to data sets. So your expected out of sample error, so the expected value over data sets of the quantity f of x minus gd of x, so minus the hypothesis produced squared, so this expected error is equal to f of x minus g bar of x squared plus variance of x, which is by definition the bias at x plus the variance at x. Okay, this is called the bias variance decomposition. It decomposes your expected out of sample error in terms of a bias plus a variance. Expected out of sample error where? At test point x. Okay. If you want, you could average this over test points. Okay, so you could take the expected value over test points. Okay, and now, okay, we have to take the expected value of this side over test points. Okay, and we have to take the expected value of this guy over test points. And since the expected value of a sum is a sum of expectations, this is the expected value of the bias of x. That's called the bias. Plus the expected value of the variance as a function of, plus the expected value of the variance over x plus the variance. And this you can think of as defining an expected out, expected E out. Okay, and expected with respect to your data sets and your test point. So this is data sets and your test point. Okay, and so this is a theorem. It says, okay, that your out of sample error, your expected out of sample error, is composed of two terms. The first is related to how, close is your average learned hypothesis to the target function. And typically, your average learned hypothesis is going to be very close to the best you can do. For linear models, yes, but in general, maybe not. But, more or less, this is capturing how well can you do. And then this is the variance of x, is saying that, even if you can do well, there's so much variance that you can't get there very often. Okay, so that's what this is saying. It's saying that you can't get there very often. So it decomposes the error in terms of how well can you do and how easy is it to find that guy. Okay, and so, you know, just by looking at this picture, it suggests that, you know, this guy can't really do well. The flat lines can't really do well, but they're consistently not doing well. So the bias will be large, but the variance is small because, you know, not much variance in terms of when you generate the data sets. On the other hand, this guy, you know, might be able to do well if you get the right data set. So in principle, it can do well. So you would expect the bias to be small, okay, but as illustrated by these two data sets, you know, the variance is huge. Okay, so let me show you some real experiments and then we'll conclude. Okay, so and an interesting question arises: which hypothesis set should you use? Okay, so which hypothesis set you should use is the one that minimizes this sum. Okay, and there's the trade-off. Okay, so the hypothesis set on the left, which is simpler, has a larger bias, smaller variance. The hypothesis set on the right, which is more complex, has a smaller bias, but larger variance. Trade-off. Approximation, generalization, trade-off. Okay, and let's see this in action. Let me show you some pictures with some real experiments. Okay, so, you know, for the scenario on the board with two data points, you know, and H0 and H1, I generated many data sets. Okay, and what we see here on the left is, you know, H0, which is constrained to use flat lines, and the flat lines vary to follow the data sets, but that's about all they can do. On the right, we have the same data sets, okay, but now the lines that fit those data are wild, and you can convince yourself that depending on where the data set, the 2 points in the data set are, and we generate them randomly. So, you know, depending on where those 2 points are, you know, the lines can produce this wild assortment of fits. Okay, and you know, so on the left, you can't really approximate well. So the bias is large, but the hypotheses are constrained, and so the predictions have low variance. They're bad, but with low variance, and that's, you know, that's seen by the bias being 0.5, and the variance is small at 0.25. On the right, you know, you get on average a better fit, which is corresponding to the fact that the lines with slope can fit the blue target function better. Okay, so the bias is significantly smaller at 0.21, but the variance, okay, the variance of the predictions are huge, and 1.69. And the theorem tells us that the out-of-sample error is the sum, and that's the trade-off. Okay, and in this particular case, H0 wins. Ta-da! Okay, so the simpler model wins by virtue of the fact that it controls the variance. Now, let's look at what happens on the right, where I'll increase the number of data points to 5 data points. The H0 seems to be behaving similarly. Okay, so it's still constrained by the fact that it has to use flat lines, so it can't approximate that well. Okay, but because we have 5 data points, the variance has also dropped a little bit. Okay, because what happens? The additional data points, the additional 3 data points now further constrain the line that you can output, because the average of 5 data points is much more stable than the average of 2 data points, and that's seen in the variance also dropping. Okay, but the bias stays approximately the same, because, you know, the bias is, roughly speaking, capturing what you can do, and on average it doesn't approximate well. Still 0.5, the variance is lower to 0.1. Okay, and so when you take the sum, 0.6. Okay, but now H1. Okay, the bias is approximately the same. You on average you can approximate just as well. So the bias is 0.21. But now look at the variance. These extra 5 points that came are constraining the hypothesis on and giving on average low variance predictions. And so the variance dropped to 0.21, and now E out is 0.42. So H1 wins. So if you were to ask me which hypothesis set is better, it depends on the number of data points. And you can view it through this bias variance approximation versus generalization trade-off. Okay. Now you might ask, well, aren't those wild lines that appeared on the left with 2 data points, aren't those also still possible? What if all 5 data points are over here? Shouldn't you also see that? Well, that's just very unlikely. That's the point. Okay. So and that's what variance captures. It's a statistical quantity that captures on average the variability, and the bias captures on average the approximability. Okay, so for the average data set, what happens with your hypothesis set? Okay, so which hypothesis is better is not a which hypothesis set is better is not a well-defined, question, because it requires you to specify n. But if we allow n to vary, then the types of behavior that you'll see are sort of typified in these two curves. So if you have a simple model, when you have a small number of data points, okay, your in-sample error and out-of-sample error are comparable, and that's what the VC analysis says, because you have a simple model, and so there's not much you can do, but it's close to E out. When you have a complex model, if you have a few data points, your in-sample error will always be lower than for the simple model, but the out-of-sample error will be huge. Okay? And it's only when you get more and more data points that the in-sample error and out-of-sample error, converge. Okay, and you get the smaller error bar, and then the out-of-sample error drops below the out-of-sample error of the simple model. So there is a number of data points above which you would choose the more complex model and below which you choose the simpler model. And let me end with just a comparison of the VC analysis and the bias variance analysis. Okay, so what does the VC analysis do? The VC analysis says that ultimately we care about E out. Okay, and what the VC analysis does, let's say for a given number of data points n, as I'm highlighting here with my arrow, it says that when you approach this problem with n data points, you're going to observe an in-sample error of E in, and then there's a generalization error bar that that relates that E in to the E out. Okay, and the in-sample error grows as you improve as you add more and more data points, because you're adding more and more constraints that have to be fit by the fixed hypothesis set. So it's going to have to, in order to fit the new data points that you've added, it's going to have to give up a little bit of its fitting ability of the old data points, and on average its ability to fit this additional information will drop, and so your in-sample error goes up, but simultaneously your out-of-sample error goes down, okay, even though the in-sample error is going up, because the generalization error bar compensates, okay, and brings the out-of-sample error closer and closer to the in-sample error. Ultimately, the generalization error bar goes to zero. Okay, the bias variance decomposition is slightly different, but accomplishes the same general idea. It takes your out-of-sample error and decomposes it into the sum of two things. Now, it's not looking at the in-sample error. It's looking at, on average, what's the error, or roughly speaking, what's how well can you do, okay? And how well can you do is this black line here. So it says that your out-of-sample error is how well you can do plus the variance that gets you up to the out-of-sample error. And now the bias variance analysis is not a bound, it's an equality. That theorem is an equality. But unfortunately, we can't compute it. Okay, so it's useful for analysis of the approximation generalization trade-off, but we can't compute it because we don't know this blue point here, this black line, which is how well can you do, okay? And also we can't compute the variance in general. So we can't compute these quantities. It's just a useful breakdown of E out. The advantage of the VC analysis is we know E in, okay? E in we can measure, and then the theory gives us this bound on the error bar, and so at least we can upper bound E out. So it gives us a concrete upper bound on E out versus a nice, clean way to analyze the out-of-sample error broken down into bias plus variance. Okay, and so with that, I'll see you next lecture.